All right, so we are going to go ahead and get started with today's webinar. Good morning. Thank you for joining our Research Radar Smart Stormwater Strategies, hosted by the Minnesota Department of Transportation and the Minnesota Local Road Research Board. My name is Molly Yang, and I'll be your host for today. So we're excited to have our presenters, John Gulliver, Andy Erickson, and Dwayne Stedland joining us today. Today's webinar is part of the Research Radar series sponsored by the MnDOT Office of Research and Innovation and the Local Road Research Board. Each month, we highlight different research projects focused on a common theme. So before we get started, I'd like to read the Tennyson warning. This session will be recorded for those who cannot attend. If you have enabled your camera during the session, the recording may include your image, which is private data under the Minnesota Government Data Practices Act. You are not required to allow MnDOT to use your image, and there are no consequences for declining to do so. To opt out of the recording, you may simply turn off your camera. So MnDOT's Office of Research and Innovation manages over 185 research projects in progress that ranges from local initiatives to pooled fund projects with other states, comprising both basic and applied research. So we're here to help transportation practitioners determine whether new research is needed or if existing studies may solve your needs, recommend the best research methodology for your project, access local and national funding sources, and manage your project from start to finish. One of our partners, the Local Road Research Board, is a city and county run organization that sponsors research and educational initiatives that address local transportation needs. So you can stay up to date with our research by following us online and subscribing to our newsletters. We'll send you website and subscription links in a follow-up email after today's webinar. If you have an idea for a new project or a problem that needs solving, we're accepting ideas on Idea Scale through April 1st, 2026. You can scan the QR code on your screen to access Idea Scale, and this will also be included in the follow-up email. With that being said, I now like to introduce today's presenters. So our first presentation on sustainable application of TDA in stormwater infiltration and treatment, we have John Gulliver. John is a professor emeritus in the University of Minnesota Department of Civil Environmental and Geoengineering, performing his research at the St. Anthony Falls Laboratory. Much of his research involves the development of new technology for the treatment of runoff and assessment of field performance of stormwater treatment practices. He is a co-author of the book Optimizing Stormwater Treatment Practices, a handbook of assessment and maintenance, published by Springer in 2013. For Stormwater BMP Inspection and Maintenance Resource Guide, we have Dr. Andy Erickson, who is a research and engineer at the University of Minnesota's St. Anthony Falls Laboratory. He studies water quality in urban watersheds, develops stormwater assessment and maintenance best practices, and designs innovative stormwater treatment technologies. And finally, for development of biochar specification criteria as soil amendment for slopes, conveyances, and stormwater treatment systems, we have Dwayne Stedland. Dwayne works in MnDOT's Office of Environmental Stewardship. He wears multiple hats in environmental compliance delivery with roles in training, stormwater management, and permit implementation. With 29 years in the field, Dwayne has dual professional certifications in erosion and sediment control and inspector to meet federal and state NPDES requirements. And with that being said, I now like to pass it on to John Gulliver to get us started.
Thank you, Millie. If you could share the first presentation. Thank you. So this, I'm going to talk about sustainable application of tire-derived aggregate in underground stormwater infiltration and treatment. These are underground chambers that you might put under a parking lot in a place where, you just don't have space to put another treatment facility. And the concept is that TDA can pull phosphate out of stormwater. And phosphate is a more difficult thing to pull out because it's dissolved. This is a project that I did along with May Kai from the Natural Resources Research Institute at the University of Minnesota Duluth, and Purnima Natarajan and Mara McCuller from the St. Anthony Falls Laboratory, University of Minnesota, Twin Cities. Next, please. So the agenda. Well, I'm going to talk about some objectives of the research and then some background on TDA. And then we'll go straight into results. Its ability to retain phosphate. What do the biofilms do? The biofilms actually stop leaching of metals, and that was a problem that we had foreseen previously. And PFAS release and absorption. Is there PFAS release or absorption? How the TDA responds to antecedent dry periods, and then cost effectiveness, and then the benefits of TDA. The two pictures here are the tire-derived aggregate, and you can see they have a lot of wires in them. Tires have a lot of wires in them, and the wires are made up mostly of iron. And iron, when it rusts, when it oxidizes, will absorb phosphate, and that's the goal here. Next, please. So our objectives, we wanted to utilize the phosphate retaining characteristics of TDA while reducing zinc and copper release with biofilms growing on the TDA. They just grow when they're in water. Other additives to mix in with TDA. I'm not going to talk about that today because we didn't need other additives. And the potential to remove or release PFAS from runoff. We did some longevity studies, studied dry periods on biofilm, and then education and outreach, which this is a part of. Next, please. So tire waste. In the USA, we put out about 3 million tires per year. We throw away 3 million tires per year. And we don't want them to end up in a dump like this here. And so we try to find other uses for them. When I get to, there's a surprising aspect to the cost effectiveness because most of it is in not sending the tires to the dump. So it affects the landfill cover due to rising because it rises, traps gases like methane and becomes hazardous. And tires also need a lot of volume if not shredded and compacted. So there's a lot of reasons to shred the tires. And then there are good things that we can do with them after we shred them. We can replace aggregate. And then it turns out that they are an aggregate replacement that actually retains phosphorus. It'll collect the phosphate. Next, please. So the benefits of TDA placement underground porosities, underground chambers. They have a high porosity, roughly 50% porosity with tire-derived aggregate. You can see some here at Walters Recycling and Reuse in Blaine. It converts tire waste into a useful resource. It has low maintenance needs because it's underground and there's really not much that can go wrong with it. It's low cost and it's lightweight. These are the advantages that people know about before this research study. Next, please. The types of TDA study was really tires chopped into between 2 and 6 inch pieces. You can see some pictures here of the traditional TDA and then TDA byproduct that we worked with called wire exposed TDA. There's no use for this TDA byproduct currently, and it's TDA with too many wires poking out of it. and that they don't want the wires to be in the TDA mixture because it will poke through impervious, it'll poke through films and things like that. So that's what we used. It's normally used in dry locations. We're talking about using it in wet locations, underground chambers to collect stormwater. Next, please. So our research results. Well, we had a bunch of buckets filled with TDA, and we're doing things with them. We had replicates and different treatments. On the right, you can see TDA in the buckets after a certain number of flushes. So we would put water in the TDA, kind of simulating what happens in an underground storage chamber or an underground infiltration chamber. You put water in, the water drains out slowly, and then it's dry for a little bit. So we would have these flushes. We had 4 flushes on the left of the right-hand set of pictures. 6 flushes in the middle and 10 flushes on the right. You can see how the biofilm is growing. That's basically a slime layer. Next, please. So in terms of phosphate retention, we did a pretty good job with our TDA. We put in phosphate, and we generally, you can see the controls are at the top at C out over C in. That's the y-axis is C out over C in, and on the x-axis is the flush number. So we'd put in a flush, and then we would save it watch it for 96 hours. Or actually 72 hours, and then we would leave it for 2 days and then do another flush. So it's a long-term study. And you can see that the C out over C in is about 0.2 for most of the treatments. That would be wire-exposed TDA and traditional TDA. We did a lid on and a lid off because we weren't sure how much exposure to the air occurs in these underground chambers. So we did both, and they both worked pretty well. Next, please. The biofilms. The biofilms growing on the TDA will retain much of the zinc, copper, and iron that's released from the TDA. We found in a previous study that TDA can release these 3 metals, but the biofilm growing on them will capture the metals that are released. And so we had virtually no metals in the effluent of these flushes. And the biofilm growth is a little bit interesting. It's pretty constant between the different flushes. It stays pretty constant. There's one TDA, traditional TDA with the lid off, which has lower biofilms, but then at the end it has the highest biofilms. We did a 1-month dry period. We did a 2-month dry period. The biofilm lives. If you've ever tried to get something out of your shower, you know that the biofilm always comes back. You have to work hard at it. And that's really what this is. It's always there. Next, please. So the biofilms do a good job. The toxic limits are in green, and the response of the biofilms are for the various treatments are in the symbols. And the influent comes in at virtually 0 zinc, but there's no leaching or a very little bit of leaching, a small amount of leaching. Iron probably had the most leaching, but iron is really not something that the PCA and the US EPA are that concerned with. It precipitates, and it probably comes out as a solid, so it's really not harmful. But the zinc and the copper are, and they are below the limits set by the EPA and the Minnesota Pollution Control Agency. So biofilms do a good job. Next, please. In PFAS, we found that there's really not anything being absorbed and nothing being released. So they're pretty much neutral with regard to PFAS. And this is a lot of different PFAS chemicals. You can see we have all the chemicals on the bottom here. There's really not much there to speak of. And so I won't speak of it. Next, please. So this is about how the PFAS is measurable, but there's relatively low absorption of PFAS to TDA. On the y-axis, we have percent PFAS reduced after 5 days. On the x-axis, we have different types of TDA, PFOS chemicals. And you can see there's a little bit of release, but most of it is absorption. 20% of the PFAS was absorbed. 10 to 15% of the PFAS was absorbed, but it's not 80%, it's not 90%, it's just a small percentage. It's not a big deal, but it's not releasing PFAS chemicals. Next, please. These mixtures, we don't really need mixtures because the biofilm works really well. Next, please. Dry periods. The biofilm was not affected by a 2-day antecedent dry period. 1 month dry period reduced biofilm, but it grew back quickly. A 2-month dry period seemed to increase the biofilm. So there is uncertainty in the response of the biofilm, but it's always there and it's always growing. Next, please. Cost effectiveness. Well, most of the benefit is in the fact that we aren't sending the tires to the dump. We're doing something useful with the tires. The value added is $273 per ton. The disposal of tires costs $240 per ton, and we're not disposing of the tires. To purchase a TDA, it's actually fairly inexpensive. And you can see it's used here as a replacement for an aggregate around an underground infiltration basin. And the other thing is that this is one of the only 2 methods out there in Minnesota that can be used to remove phosphate. And phosphate's an important chemical. It's important for us to limit the phosphate release because phosphate is the limiting nutrient for algae in ponds. If you have too much phosphate, you have a green pond, a green lake, a green river, and that's not something we want. And so we want to control phosphate because it's a limiting nutrient. They have enough nitrogen, enough of everything else they need, enough potassium. All they need is phosphate, and they'll grow like crazy. We don't want them to grow like crazy. We want a kind of a clean water body. The way to do that is to remove phosphate. And right now we can only do it with an iron enhanced sand filter. This is another technique that can be used. So I think that's my last slide. Do we have questions, or are we saving those for the last?
We'll be saving questions for the very end. Yep.
Okay.
Okay.
All right, I can take over. Welcome again. My name is Andy Erickson. I'm so excited to be here to present for you today. My screen should be coming up here momentarily. I'm going to talk about updating the Minnesota Stormwater Inspection and Maintenance Resource Guide. Hopefully you're all seeing my slides. I'm going to have some links I'll drop in the chat here in a little bit. But again, my name is Andy Erickson. I'm at St. Anthony Falls Laboratory, part of the University of Minnesota. This was a project that was funded through the local Road Research Board of Minnesota. I'll talk about that again at the end. But what we're talking about is stormwater treatment practices. And there are many different types of stormwater treatment practices. You can see several of them pictured here, whether they're filters or stormwater ponds or even dry detention basins or bioretention rain gardens. These stormwater treatment practices also go by many names and acronyms. I have many of them listed across the top. You are a stormwater rock star if you know what all of these stand for. But we use a lot of different types of nomenclature in the stormwater world, and oftentimes some are used interchangeably and possibly incorrectly. And that creates a lot of confusion amongst the stormwater professional world. So one of the things we tried to do with the manual that I'm going to talk about is be very clear and specific about what we're talking about. What is a biofilter? What is a bioinfiltration practice? What is a filter? What is a wet pond? What is a dry pond, etc. So nomenclature, terminology is very important in this world. And I probably don't need to explain this to this group, but our stormwater treatment practices, or BMPs as they are often called, are out in the environment. They're in nature. They are not protected from the elements. And Mother Nature can wreak havoc really on many of these things. So that is a challenge when we're trying to think about how to keep these practices working long term, and why effective maintenance is essential. There are many different types of stormwater treatment practices, as I just showed on the previous slide. They come not only in many different types, but many sizes, and the sites into which we install them are all different. So there's many variables that go into each individual stormwater treatment practice, and then the maintenance to keep them functional then must be specific to that site and that treatment practice. And something we rely on our stormwater treatment practices pretty regularly is that for them to operate independently. These are passive treatment systems. We build them and then we walk away. We let them sit out in nature and they do their thing. They don't have an operator that's standing by. They're not in controlled conditions like a wastewater treatment plant or a drinking water treatment plant. There's not all kinds of gauges and valves and dials we can turn to optimize performance. They are passive systems installed in the environment in a variety of different ways at a variety of different sites, and we are expecting them to function long term. That assumes effective maintenance. Without maintenance, we all know without maintenance, things fail. If we don't maintain our vehicles, they're going to break down. If we don't maintain our homes, things are going to break. The same is true of our stormwater treatment practices. And maintenance is actually a large part of the lifetime costs of stormwater treatment practices. You might not realize that we have some data that I'm not going to share today, but it's in the manual, and we can share it outside of the time that we have together today. But depending on the size and the type of practice that you install in terms of a stormwater treatment practice, your maintenance costs can eclipse your original construction costs within 5 years. Meaning if you spend, $10,000 to build some rain gardens in front yards, within 5 years, you may have spent $10,000 on maintenance. And years 6 and beyond, now that cumulative maintenance cost is actually more than you invested in the original construction. So it's important to plan for maintenance. It's important to budget for maintenance. And if you're not sure what to put in your budgets for maintenance, again, we have numbers for you. And I'll talk about that again at the end of the presentation. But for all of these reasons, effective maintenance is essential to keep these stormwater treatment practices functioning. But you might ask, why do we need a stormwater inspection and maintenance resource guide? Isn't all of this information already out there? And you might look to the Minnesota Stormwater Manual, which is the standard for design guidance in Minnesota. It also includes all of the regulatory requirements for Minnesota as it relates to stormwater management, and it does include maintenance guidance. However, some of the feedback we've heard from stormwater professionals and especially MnDOT, who funded this work through the Local Road Research Board and the Local Road Research Board staff, it can be very hard to find exactly what you're looking for in the Minnesota Stormwater Manual. There's something like 8,000 individual pages of the manual. So when you're looking for maintenance of a rain garden and you're really focused on phosphorus removal, it can be somewhat hard to find that specific piece of information. And that's why the Local Road Research Board funded a project to build a specific to stormwater inspection and maintenance resource guide. And ideally, clear, concise resource guide that people can use and find what they need very, very quickly. So What is operation and maintenance? And again, maybe this is familiar to you, maybe it's not, but the terminology is important. And that's why we want to define some of these terms. When we talk about inspection, we are talking about very quick, simple, visual assessments to select and schedule maintenance. We want to know what's wrong with the practice, and we want to know what maintenance is needed to fix it. That is inspection. That is its purpose. It also is intended to be very quick and simple, and actually low training. When we get to the inspection forms at the end of this document, you won't get to see the entire form, but we devised these forms that you could train interns, summer interns, to go out and do these inspections for you and really collect a lot of data very quickly, possibly for all of your stormwater treatment practices within your jurisdiction. That is the ideal, that it's that quick, that simple, and it's a visual assessment. An assessment actually can go beyond inspection. You can actually do additional measurements to help refine and further select and schedule your maintenance. But you can see that both of these are geared at the maintenance. The maintenance is the key piece because those are the activities that are ensuring the proper function and extending the usable life of our stormwater treatment practices. So ideally, we can do quick, simple visual inspections to select and schedule maintenance. We can also determine if we need additional, more rigorous assessment, which is a measurement of the performance, to select and schedule maintenance. And then we recommend maintenance to then correct any issues that we might find in order to extend the life and ensure the proper function of these treatment practices. Now, when we talk about maintenance, we've broken maintenance up into 3 categories. And I think of it like a pyramid because foundational to all of our maintenance is routine maintenance. This is relatively regular and relatively frequent maintenance. These are things like doing your visual inspections. That should be a regular occurrence and it should be relatively frequent compared to other maintenance that we'll talk about shortly. It might also include litter and debris removal. It might include vegetation and ground cover management. Again, almost every year the vegetation grows up pretty well and you need to maintain that in order to make sure you have the right vegetation in place. The vegetation is where it belongs and not where it doesn't belong, that the vegetation is not preventing you from doing critical maintenance on your practice. So that is a regular and relatively frequent routine maintenance activity. But then above that then is what we would call non-routine maintenance. These are things that are triggered by specific observations. These are, if it's broke, then you go fix it. And if it's not broke, you don't fix it. That's what non-routine maintenance is all about. It should be, ideally, in an ideal world, relatively infrequent and certainly irregular. We don't expect to do non-routine maintenance every month or every season or even every year. It should only happen when it's needed. Now, if some non-routine maintenance, such as structural repairs, are needed on a relatively frequent basis and are pretty regular in their scheduling, you might want to look at the cause of that. Especially structural repairs like flared end sections or inlets or outlets or things like that. If they're getting damaged, if something like that is occurring and you need to do some real structural replacement, look at that and find out why and adjust the cause. It will significantly decrease your maintenance costs if you can focus on your routine maintenance and only do non-routine maintenance when you need it at a relatively irregular and infrequent basis. When we put these together, we have what we call preventative maintenance. If you're doing your routine maintenance and you're triggering your non-routine maintenance when you need it at the appropriate time, you're not coming in way after it needs to be done, ideally, you're going to prevent the major maintenance, the complete rehabilitation or complete rebuilding of the practices, because this is where most of the cost will come in. If you have to rebuild a rain garden or a sand filter or even a stormwater pond, it's very expensive to rebuild it because it's a retrofit at that point. The project is done and the contractors are long gone. You have to come in and try to rebuild that practice within this relatively confined, limited space. And that's often way more expensive than the original construction. So if we can prevent our major maintenance activities by doing our regular routine maintenance and our irregular non-routine maintenance, we're going to save a lot of money in the long run, and these practices will perform more consistently for their entire lifespan. So what did we do with this maintenance, inspection maintenance resource guide? We actually have a number of sections in the guide because there are a number of stormwater treatment practices. We did build upon past learnings and past research that we and others have done, but we also added new practices. Since some of the prior maintenance and inspection guidance that's come out has been published, there's some new things going on in Minnesota, and we need to address those with good guidance on inspection and maintenance. When we talk about ponds and wetlands, floating treatment wetlands are a new practice that's being installed, and people are wondering, how do I inspect this? How do I maintain it? What do I need to know about these that's different than some of our other treatment practices? In addition to our constructed stormwater ponds, our constructed wetlands, those are a new practice. When we talk about underground sedimentation practices, things like sump catch basins, wet vaults, aggregate pits, proprietary settling devices, we have inspection and maintenance guidance there, although many of the proprietary products come with their own maintenance guide that's specific to that proprietary unit. Thinking about infiltration practices, things like infiltration basins and rain gardens, the implementation of MIDS has driven, and even prior to MIDS, many of our practices are now infiltration practices, and they need unique maintenance and inspection activities to keep them functioning. One of the recent advances or new technologies that we're seeing in many of our urban landscapes are tree boxes and tree trenches. How do you inspect those? How do you maintain those? Filtration practices, again, there's been a number of filters, and in fact, we've been using filters for thousands of years to treat water, not necessarily stormwater, but to treat water. But the more recent advancements are amendments to sand filters. Things like the iron enhanced sand filter or a biochar enhanced sand filter. How does inspection and maintenance change for those amended sand filter products? And what do we need to know differently about those types of practices? Bioretention practices or biologically enhanced practices. These are practices that really rely on vegetation to help with the function. Things like rain gardens, bioswales, even some infiltration basins that are more vegetated than maybe sandier ones. There's a little bit different inspection and maintenance because the vegetation is very important. So we need to inspect the vegetation. We need to select maintenance activities that are appropriate for the type of vegetation that's intended to be there and where it's intended to be. Full depth permeable pavements. So that's also kind of a category of products that are relatively newer in Minnesota, at least in the last 1 or 2 decades. We have a lot more permeable pavements in Minnesota than we did prior to that. So whether it's pervious concrete, porous asphalt, interlocking concrete pavements, or block pavers, there are inspection and maintenance guides for that. And another new one is stormwater harvesting. So we are using stormwater harvesting and reuse for a variety of different end uses, whether that's flushing toilets or irrigation. Inspection and maintenance on that is a little bit different. However, many of those are very site specific. They are designed specifically for that location. And again, many manufacturers or installers will provide a maintenance guide with it, but we have some case studies of what that looks like if you're interested before you make a decision to go that direction. Now, in each of those sections, those are different types of treatment practices and how we generally have it organized. In each section, we talk about the benefits and the limitations of those practices. We talk about the different assessment activities. How is visual inspection different? What are some additional assessment methods you might incorporate when needed? For example, capacity testing or synthetic runoff testing or even field monitoring. We also talk about the factors that affect performance. In other words, what are the maintenance triggers? Why is maintenance often needed on these types of practices? And that is different based on each practice. And then I think what a lot of people are super interested in is how much is it going to cost? I think a lot of our budgets at the municipal level, even the watershed district level, anywhere that people are maintaining these things, it can be a little difficult to come up with good numbers of how much you think maintenance is going to cost. We've pulled together the literature, we've pulled together the research, we've synthesized that down into some projections so that you can put those into your budgets and hopefully provide plenty of money to do the most appropriate maintenance for your practices. Another new section in this maintenance guide that's different than other guides is what we call meeting stormwater management objectives from the inspection and maintenance perspective. And what I mean by this is if your goal is blank reduction, whether that's sediment, phosphorus, metals, organics, or pathogens, your inspection and maintenance might be different So we have a section on meeting stormwater management goals where you can go in and say, I'm going to look at phosphorus because that's my primary goal in my particular watershed, or for these particular stormwater treatment practices. I'm going to go there, and then this section is going to tell you what you need to focus on in terms of inspection and maintenance for XYZ practices or activities. So a little bit different perspective, but I know a lot of our stormwater practitioners are coming from that perspective. They might not even know how to choose what practice to use. This can help you go that direction as well. So to give you a glimpse of what it looks like, we developed inspection checklists. Again, these have been around. We've revised them and updated them with the most recent state-of-the-art and state-of-the-science information on inspection and maintenance. They look something like this. They are a PDF fillable form. You can print them and write on them. You can have them on a tablet or a computer, and you can type and tap and checkbox to make it work. You can also upload photos and things as needed. And we cover all of these different types of practices. Again, some of the ones we've already talked about before. We have an inspection form for each of these. This is intended to be a resource for you. So if it doesn't match exactly what you need, if you need some other information, or if there's questions here that really don't apply to you, that's fine. Take them out, skip them, add to it. It's meant to be a resource. You are welcome to take them and change them however you need to. All we ask is that you give us credit as we originally developed them, but they are intended for you to use them, and they are freely available. Going along with the inspection checklist is once you fill out the form, you might not know, well, what do I do with this? I've checked it, I've filled it all out, I've identified all these things. What do I do now? We have maintenance tables, maintenance activities. So for each question in the form, you go to the section in the maintenance table of that question, and you say, okay, I answered this, and this on this question for my inlet structures. They were clogged. We see some spalling of concrete. Then it tells you the maintenance activities to do to fix that problem. So you almost have to know, you can know almost nothing about these stormwater treatment practices, and then this literally will walk you through step by step from inspection to recommending maintenance activities. So just to kind of sum up quickly, we published this last year in June of 2024. There's a QR code here. There's a link here. I'm actually going to drop that link in the chat as well. But I'm going to come back to this slide in a minute at the end when I get to questions. So if I go past the QR code and you haven't seen it yet, that's fine. We're going to have this up again. We cover a wide variety of stormwater practices. We cover inspection, assessment, and maintenance resources. There are PDF fillable forms, and we talk about the maintenance triggers, the activities, and the frequency and cost of these maintenance activities. So let me drop this link in the chat. There we go. And the only other thing I just want to say before I hand it off to Dwayne, if this was useful and interesting to you, we have an email newsletter you can sign up for. It's called Stormwater Updates. You can find it at our website here. You will also find on the website all of our publications, including a link to this resource guide. So again, if you missed it, that's fine. You can find it online. You can email me. I can send you a link. I can send it directly. There are lots of ways to get the information. We try to make this information as accessible to everybody as possible. And finally, we also host a Minnesota Stormwater Seminar Series. So if you don't want to just sit and read a long manual to learn some things, tune into our seminar series. We have a national speaker to give a keynote talk on the most innovative green infrastructure and stormwater management technologies and knowledge that we know today. We then put them on a panel with local Minnesota experts, because the Minnesota context is very important. You can find us online. We have a schedule. We actually have a YouTube channel where all of our past seminars are recorded and on YouTube. So if you see someone here that you would have loved to seen, don't worry, you can find it online. I also encourage you to check out the website for the future schedule. We have some very exciting seminars coming up. So I'm going to throw this up one more time. I'm also going to drop my contact information in the chat, and I will drop our stormwater website link into the chat as well. But I think with that, I'm going to stop sharing and I'm going to turn it over to Dwayne. Thank you so much.
Thank you. My name is Dwayne, and I want to say thanks to everyone that's really helped me. That'd be Mei-Jun Kai and Dr. Brian Berry. There's just a lot of people that I'm exceptionally grateful for. Thank you for this opportunity to present. I believe biochar is going to be, it's not going to solve all problems, but it's going to be one of the most important things that I've ever had the chance to work on for solving an awful lot of the stormwater problems I'm having. And I believe for climate resiliency and storms that are more intense, more frequent, and more weird. So the agenda is what we need to know about biochar. I'm not sure what people do know, what I'm trying to solve. And by the way, Millie, if you need me to stop, just say stop. I know we're running out of time, but just the way it is. What we have found, I'm hoping, and the next steps, I can tell you that biochar is real. It lasts for a very long time. You can argue that even the little thing that we had on Earth a few million years ago did form biochar because we can still find it. That's how fascinating this is. But this is not the kind that I want to talk about. We can also talk about this as forming biochar, but this is not the kind that we want to talk about either. Um, and thanks to Stefan, that if we don't reduce this, because so part of the reason for biochar today is we have an awful lot of black ash and green ash that are dying. We have an awful lot of storm damaged trees. And rather than let them accumulate and create an amazing amount of biofuels for intensifying fires, to instead would be to harvest some of that dead wood material, not all, but maybe during the forest harvest. That's an example. And certainly in the metro area, DOT has a lot of dead trees, and to create another beneficial material out of that. So that is sort of like a char. That's that brown material. And we know that in the Midwest, including Minnesota, that prairie fires were used for years before certain colonizations of people came in after the tribal communities. So there's been a lot of value in this for maintaining ecosystems. So this is just an example of the St. Croix Travel Information Center where we do burn. This doesn't necessarily make biochar, but it does help maintain healthy environments. So if I can't burn, could I add something else that mimics a burn? And that's where the biochars could come in. So what is it? It's basically defined as a thermochemical conversion of biomass in an oxygen-limited environment. So what you have left is cells. So these would be a great way for making biofilms. This is a bacteria on apartments is what I look at it. It will retain water. It's good for heavy metals. I'm hoping that it'll be good for 6-ppdq, the quinones off of tires. We don't think it does much for phosphorus. We don't think it does much for PFOS, but it still might create the environment. So this is in the city of Woodbury. We know an awful lot about this. You can make them yourselves. Instead of having campfires, have a biochar fire. And city of Minneapolis is in construction right now to deal with some of their wood waste material. It's currently in construction. This is the Gopher Stadium, and this is where the facility will be located. And I think it's really important that they're creating a system that they hope to use all the material that they generate. And there's a value for this. Just an example of the equipment, it's not a big deal. This is something I saw at the Biochar conference. This can produce 12 tons an hour. And why is this a big deal? Well, I need to make sure that I have standards. And I don't know exactly what it'll look like in the future for the standards material specification, but I hope to be able to use it for general use, and that would include carbon offsets during construction, landscaping, topsoil, stormwater, certainly hydrocarbon mitigation, heavy metal sequestration, a whole bunch of really neat things. That's why this is really quite exciting to me. So the first round of research, called phase 1, was to basically characterize the char. Because right now, anyone can say anything about anything and say, nope, mine is 600-degree char, and they don't really know. So this is a way of getting you defining certain temperatures and verifying that the material works as stated. Because we need to solve a problem, and it can't be just because someone wants to sell it to us. So I really are trying to use local materials. That would be black ash, hardwoods, but it doesn't mean softwoods can't be used. And by the way, it could be used for just about anything organic, whether it's agricultural waste or waste that would normally go to a landfill that would produce methanes and other materials. So we are hoping that we can generate something. But I'm starting off with hardwoods because it's really complicated to look at all biochars and say they're all equal. And that's the whole point here. So these are some of the things that we're really trying to figure out is how do you have a product that you can test and have a uniform product that will perform in the way expected by the owner. The designers and the construction can install it. Construction can make money because we are a capitalistic system, and it can be measured by those that are out in the field by inspectors and engineers. So we want to make sure that we have a uniform material, that we have as large of pores as possible, and something that people can make on our behalf. So the research in a nutshell is we looked at a whole bunch of different temperature ranges looking for the optimum material. So this is a very precise biochar production system up at in a Duluth, Hermantown area. And these are the temperatures. So we're really trying to find the right temperature that gives us the maximum values for solving something. So we really want to make sure that we have, this is other research, but the idea that you have certain pore sizes that help us to, again, store heavy metals. Again, it doesn't do much for phosphorus, but it may do an awful lot of other benefits for rhizosphere organisms and so on. So we're really looking for this value, and I'm going to start looking at 650 degrees because in almost all cases from the research, so we want maximum carbon, minimum ash, because ash is a liming agent. That's not what we're looking for. So again, I try to put these numbers on the graphs of the final report of phase 1, and it really looks like 650 is coming out as basically a perfect temperature for a lot of different reasons. Water holding capacity is a pretty important thing. Yeah, you can go much further on it, but 650 still works. We're looking for that pore volume. There's a lot of reasons for that pore volume, and they're able to show us. So this is where the black ash, it's superior. And that's why we're trying to say that not all biochars are the same. And we don't know where all these other chars from agricultural materials for railroad ties, you name it, where they fit in this line. But we know black ash gives us a very good total pore size. And this is why we're looking at hardwoods right now, because there is a black ash problem. And the data doesn't really matter, just that 650 come out as a really good number. And again, for water holding capacity, I believe this is carbon to carbon organics, but we're really looking at trying to make sure that we can get certain metals, chromium, nickel, zinc, lead, and I'm looking at arsenic and other materials that will have maximum. So it's clear that not all metals react equally well to various temperatures or precision temperatures. And again, our goal is not to use activated carbon. That's certainly a benefit, but we're trying to use resources that we have. Phase 2 is going further than that, and now that is to try to design gains. So phase 1 is to develop the material spec. The phase 2 is to find out does it really work, and then develop the design manual. So that's the phase 1, phase 2. And this is what I've already developed for those that are interested. People are asking me like crazy, you got a spec? So these are examples that are derived from phase 1, working with the university group, of carbon sequestration, basically a basic additive that would be road-based. You'd be surprised how this stuff is amazing as even concrete or Portland cement replacement. General additives, and this is where it would fall into my temporary sediment control. Nutrient enhanced additives. This might be for our landscaping community, trees, shrubs, and even native plants in stormwater boulevards, stormwater treatment additives to do very specific things. And believe it or not, it's used as a food additive. And I won't be regulating, but I do have a class for it already in case that's what the industry wants, but they're going to follow the FDA certification program, not anything that I would write. So it's the same material. What changes is the degree of testing. That's the results thus far. So it'll still be hardwood, let's say. And so it's not multiple sources. It's hardwood, let's say black ash. And then the degree of testing. So as the testing goes up, the cost goes up. And so then now, this is you can't read it, doesn't matter. It's what it's to tell you or tell me is that I'm trying to find, does anyone in the world have a design manual? So if I've got a standard spec, now I need to figure out how to design for it to solve problems. So DOT's even responded. So it's actually been a very good return on this investment. So this is a consultant through the research office again to find out is anybody anywhere using this stuff. So we've got Australia, various DOTs. It's been a really fun process that's not been finalized yet, and it doesn't look promising for a design manual, even though the United States Biochar Initiative is doing something. The Chesapeake Bay area is doing something. I just can't find much on it. But the point is, I really am interested in heavy metal removal and first flush off of the roads. And again, this biochar is quite promising. It's not universally promising for all metals, but it's really promising. So in the few minutes that I have left, and maybe I've already burned them up, is that to show you how I'm using it already. And that is for daily covers, filter logs, soil coatings, and soil covers when you're working in soils that have known contaminants. And so in Minnesota DOT, we might have soils that have various heavy metals, and we'll have your green soils, yellow soils, and red soils. The red always go to some designated approved landfill. And then we've got a lot of other organics besides metals that might be in sort of called yellow soils. And how do you handle them during the excavation, temporary storage, and then final disposal or final reuse? And this is what I'm trying to get at. So this represents Moorhead, and thank you, Kelsey, and others that are with us today, is that you have these various plumes. And today we're digging in places where I was on the project yesterday, and oh my goodness, some of the smells were just amazing to me. So what are we going to do when it can't fall back into our treatment system? So we need material performance properties. So it solves a problem. It's not just buying something, it needs to solve something. What's the point of the research? And thank you for everyone that's helped me on this. So I'm going to predict in the future it's going to be for carbon offset for construction. We generate it takes a lot of energy to build something. It takes a lot of energy to make Portland cement. In fact, it's probably going to be it already is, an additive to Portland cement. So it's more than just fly ash as a replacement, but it could be. So it's really fascinating how these chars are likely to end up in pavement, both bituminous, but probably not Minnesota, and certainly Portland cement. But anyway, we have to remove a lot of trees. And and I want to use the trees during construction, and anything that's left as waste to convert that into biochar and put it back onto the project. So that's the goal here. And so I'm going to talk a little bit on the concept of using it as a soil amendment. So this is an active project, and those red things are char-filled sediment control logs, because this stockpile in the back here is the contaminated soil that does have certain constituents that, of course, when you drive into a storage area, a stockpile, or drive out, you're always tracking something. So it's trying to make sure that that doesn't end up into the stormwater system. So thank you for those that help make this technology available. It's not part of the contract yet, but that's why I need standard material specs. And so the examples of all these contaminated areas is Hazing Away, because that's this log back in Moorhead. This is certainly a contaminated soil, and trying to have engineered systems, logs that will treat this material before it goes into a curb gutter, pipe, and water resource. So they could be char checks. And by the way, this one is just for pH. It's interesting in what we can do with char checks. So it's got biochar in it. You know, char inlets, rings, and pillows. And I'm hoping that someone will invent for me a char drop bag inlet for these things in the future. Char mats, which would be for our exits. It could be mixed with aggregate, wood chips, or even these engineered systems, so that if it rains, this material is bound to the char. And all of that will eventually be disposed of, but in the meantime, it's trying to keep it that normally would be just flushing off into the curb gutter, would be sequestered here long enough for us to get the project built. It already being added to char mulches. You know, it's just mulch, but add to various hydromulches. And this is a very good thing. Again, it'll help sequester. There are already multiple blended materials, and why not char in them? And I call this hydrochar. And this might be applied to soaps that have the potential to erode deleterious materials. It might be included in the flock. So I think the future on chars are just amazing. You know, char dewatering for filter material, char synergy with other BMPs, particularly with dewatering and pH neutralization. This is just an example. Certainly added into engineered dumpsters and so on, using char for stormwater quality. It might even be a benefit, with the idea of biofilms and enhancing biofilms and tire-derived aggregates. The future is just ours. And so my real goal is to be able to add a certain amount of char to the inslope to be the first flush treatment of whatever falls off the road. That would be the tire residue of 6 ppdqs, zinc, copper, from cars, chromium, all the things that come off the cars. And our horsepower worker is actually the inslope that looks just like green space before it even gets to the conveyance system, before it even gets to the stormwater pond, and actually having designs of where it would be incorporated. And there's a lot of research that's being requested to look at this. So I'm very excited to say thank you for your support.
Awesome. Thank you, Dwayne, for wrapping us up. And we still have a few minutes for questions. So if anyone has any questions, feel free to unmute yourselves or drop your questions in the chat. And I think, Dwayne, we might have one for you already, from Gladys. They asked, would basalt be useful?
A great question. And salt is might be useful for de-icing, but char will likely do nothing for salt, because it has to be You know, the constituents of sodium or chloride or mag or calcium, you have to be bound to something, and it's a salt and it freely flows through. That doesn't mean though that we can't create plant roots that the biochar will help facilitate chloride retention or sodium retention, but in of itself, nothing on salt.
Oh, and I think just to clarify, it's basalt. I'm
Oh,
thinking, yes. So they're asking if basalt would be useful.
well, again, anything, if the question is, will basalt actually store something of concern? Well, then absolutely yes. So I think, you know, Andy has done a great job on the manual, and we've only just been able to add soil soil additives to enhance the property. So we already know about iron. We've succeeded on that iron enhanced. So we've got iron enhanced sand filters, but sand itself doesn't do much. So we know roots do something, and we know additives. So I think the future is going to be amazing recipes. So as Andy said earlier, if your concern is nitrogen, if your concern is arsenic, that we are now getting to the point where we can add specific constituents. So if basalt does something, after research, well then by golly, yes, we'd want some basalt in there with our chars and every other, media additives to solve problems.
Thank you, Dwayne.
And that includes, Andy, peat or compost. So you're worried about compost? No, I'm not. But we might be able to add something to compost that will eliminate the phosphorus claim, or add it to pond cleanout mud that I could reuse the material in a beneficial upland manner, rather than landfilling or losing it to someplace else. I just think it's cool. Stay tuned.
Yeah. Great. Any other questions? Well, John, I actually have a question for you when it comes to tire-derived aggregates. I'm curious if there are any existing regulations or guidelines for using that, because a lot of your research is testing whether to tire-derived aggregates have long-term benefits. But what about application right now? Are there any applications in the field going on?
There are a few applications. It is not prescribed. It's not a prescribed technique in the Minnesota Stormwater Manual, but if you want to put in an underground facility that's an infiltration facility, the MPCA will allow it in general. They will allow it. They won't say that we need this. They won't say that you should do this. But when you put through the design and through the MPCA, they will allow tire-derived aggregate. And there are a few applications around.
Yeah.
I also want to add one more thing, Meili, that if we're trying to use local resources to make the biochar, so bringing a production facility to the Northwoods with an air curtain type char production facility, and then use it locally, is trying to minimize shipping and transportation of products that are already in Minnesota and are already a problem.
Mm.
The wood waste from construction or other organics, or wood death because of insect infestation, likely due to warming at temperatures and weirder weather.
Right, right. Mm. Well, we are up for time. So I would just like to thank everyone for attending. Thank you to Andy, John, and Dwayne for your presenting your important research on stormwater treatment systems. After today's webinar, we will send you all follow-up email with resources and everything that's been shared today. And again, thank you all so much for attending. Great. Hope you all have a great rest of your day.
Thank you.
Thank you.
Thank you.